experimental exploration of magnetic quantum phase transitions in germanium quantum dots.
Hello, everybody. My name is Stefano Reale, and today with my colleague Zhang, we will present our recent result on quantum simulation performed on a 2x4 quantum dot ladder. First of all, I will start with a brief introduction on our system. We work on quantum dot spin qubits, or spins in general, and we have a very rich Hamiltonian that we can use to perform quantum simulation. First of all, we can electrically tune in situ this potential between dots, but also the tunnel coupling over a pretty large range of parameters. And then our system is characterized by an on-site potential and also a long-range Coulomb interaction. And critically, we can reach a regime where, using dilution fridges, we can reach a regime where our tunnel coupling and our on-site energy is much larger than our thermal energy. And by doing this, we were able to demonstrate different effects. So for example, we can work in a regime where the on-site energy is dominating. And here we demonstrated a transition from a metal to a MOT insulator phase. But we can also work in a regime where the tunnel coupling is dominating. And here we demonstrated for the first time Nagaoka ferromagnetism. And we can work also in a regime where the exchange coupling is dominating. And finally, a regime where the Coulomb interaction is dominating. And here we perform a Coulomb drag experiment on exciton pairs. But today we are going to focus mainly on the regime where the exchange interaction is dominating. We decided to work on germanium spin qubits. And this is because for two main reasons. The first one is that they possess a low effective mass, like the holes in this system possess a low effective mass, and this eases the fabrication and also eases the simultaneous interaction between neighboring dots. And moreover, the second property is that they possess spin-orbit coupling, and this gives rise to anti-crossing that, as you will see, we can exploit to perform our experiment. So I will present my result on the beam splitter interferometry for many-body spectroscopy, while Xin will present later his result on synthesizing dimer-Asch quantum magnets. OK, my talk is divided mainly in 4 parts. I will start explaining what is beam splitter interferometry, how we initialize the system, and then the result that we obtain for different spin chains. And finally, I will conclude with the analysis on the energy level statistic. But this project started with the question that we ask ourselves, can we obtain the full many-body spectrum with a one-to-one mapping to the intuitive computational basis? So a bit of explanation on the beam splitting or Ramsey interferometry. So the idea is that we prepare a superposition on a single spin in the computational basis. Then we adiabatically evolve our system to the Hamiltonian that we are interested to study. We perform some phase pickup, and then we adiabatically evolve back to the computational basis. And by changing the time tau that we spend in the, let's say, in the Hamiltonian of interest, we can reproject then the superposition back and read out the phase accumulation that we had in this regime. And by doing this, we can see this oscillation. And this oscillation, once we take the Fourier transform, give us exactly the energy difference between the two states that we prepare in superposition. To prepare the superposition, we use this anti-crossing that is given by the spin-orbit coupling. So you can imagine that we can initialize every pair of dots by highly detuning them. So we are in a regime where we have 2 holes in the same dot. And in this regime, the singlet is much more favorable than the triplet. And so we can initialize a singlet state. And then by ramping instead to a regime where the potential are equilibrated, we go to instead to the Zeeman basis. And by changing the ramping time, we can prepare different states. So for example, if we ramp very quickly to the regime, we go diabatically, and so we maintain the singlet state. but the singlet state in the balanced regime is not a good eigenstate, and so we see oscillation between the down-up and up-down state. And this oscillation, you can see it here. But instead, on the opposite case, if we go very slowly, we map our singlet into the down-down state. And this is a good eigenstate, and we lose oscillations. And this is possible to see at the end of this graph, or this plot. But instead, if we go in an intermediate regime, we can prepare a superposition between the down-down state and the down-up state. But this is nothing else than a superposition of a single spin. And this is what we can use to prepare the superposition that we want. In a similar fashion, we can do a swap. And so we can swap the superposition to the other spin in the pair. And by doing this, we can obtain the full spectrum as a function of the interaction energy, which in our case is a Heisenberg exchange. We can do this also for higher, like for a larger number of dots. So this is the result that we obtain for a 4-spin chain, where each number corresponds to the spin that we prepare in superposition. And, but we can also extend this technique to measure higher manifolds, so higher spin excitation. And we do this by preparing our system with one spin up and one in superposition. And then by summing the obtained frequency to the one that we obtained before of the first manifold, we can reconstruct also the higher manifold, higher spin manifold. And with this one, we can reconstruct ideally the full spectrum. And these are the results that we obtain. And as you can see, they closely match the theoretical spectrum. OK, we can do this for the full array. So here we defined this spin chain composed by 8 quantum dots. And here we have a lot of states, so it's very time-consuming to get the full spectrum. But we decided to extract the full spectrum at 3 different regimes of exchange. So we have the regime with no exchange, so isolated case, and then what we call the medium exchange and large exchange. And these medium and large are compared to the, let's say, intrinsic disorder of the system that for us is given by the difference in Zeeman energy. And these are the results of the spectra extracted at these different regimes. And from this, we decided to do a study on the level statistic. So we wanted to try to reveal this transition from localization to chaos. And to do this, we did two different analyses. One is the level statistic analysis. And from this, we should see a transition from a Poisson distribution to instead a Gaussian unitary ensemble distribution. Because you can imagine that when the system is strongly interacting and is overcoming the disorder, we should see some level repulsion. And this level repulsion should be reflected in this probability that, let's say, from Poisson, where the probability of having small distance spacing is very high, instead we should go to a distribution where the probability of having degeneracy is very small. And the same is possible to see it on the spectral form factor, which is nothing else than the Fourier transform of this level statistic. OK, so with this, I hope I convinced you that we were able to obtain a one-to-one mapping from the computational basis to the many-body spectrum. And in future, we could extend this kind of experiment to also study the dynamic of the system. And yes, this is the first realization or the first signature of localization to chaos transition in a quantum dot system. And with this, I would like you to thank you and thank my collaborator. And thank you for your attention. And I will give the word to Xin.
Device as Stefano has used to simulate quantum magnetism in real materials. So in the figure on the right, you see that this is a dimerized quantum magnets in the materials that we want to simulate. So what is dimerized quantum magnets? Actually, if you can think about it, if you have two spins, if they are strongly coupled, it is like a spin dimer. And you can, in a real material, if these spin dimers are weakly coupled, that they don't destroy the spin dimers, and you can call it a dimerized quantum magnet. The geometry can be very flexible. It can be like a ladder, like a one-dimensional chain, and two-dimensional, three-dimensional. The black picture shows that we have a real material. It's a thulium-copper colloid, where the copper ions, they are strongly coupled via the superexchange of the colorides. And these copper ions dimers, they are weakly coupled with one another. And what's interesting about this material is that these kind of materials, if you're changing the external magnetic field, you will see they will behave Bose-Einstein condensate behaviors. So how does this happen in fermionic system, you may ask? Actually, this can be traced back to 1956, where the theorists from Japan, they realized that the Hamiltonian of a vector spins that are subject to an external magnetic field can be mapped to the Hamiltonian of a bosons that behave Bose-Einstein condensation. To be more exact, this is I can give an example of like a spin ladder. So here the vertical coupling is very strong, the J perpendicular, and you have spin dimers along the runs of the ladder. And they are weakly coupled by the horizontal exchange coupling J parallel. You can easily write down the Heisenberg Hamiltonian that you have vertical couplings, the blue one, and the yellow one shows that we have weak horizontal exchange couplings. When we map this model to the boson model, actually here this is the hardcore boson model, you will see that the vertical exchange coupling and the Z energy, they are controlling the chemical potential of the bosons on the sides. So here we call this spin gap. Actually, this is a spin gap between singlet and the T minus, the lowest triplet state in the system. And others, the mapping is like the weakly coupled J parallel, they are converted to the tunnel couplings and the repulsions in the boson system. So here, to simplify it, so we can mapping the bosons with the spin dimers. And if you have a singlet in the spin dimer, it means that there is no boson on the side. If there's a T minus in the spin dimer, it means that you have a triplet, you have a boson on the side. Usually, when we changing the external magnetic field, you are changing the spin gap energy. Actually, you are changing the chemical potential of the bosons in the system. So to be more detailed in this picture is that, for example, if the B field is very small, you have a very strong spin gap, and the ground state is a singlet. And if you increase the B field, you have more triplet in the system. It forms canted antiferromagnetic states. And this also means that you are starting populating bosons on your empty sites in the array, which give you a Bose-Einstein condensate. After that, if you increase the B field more, you can see that all the spins are polarized in the same directions. It also means that the bosons are occupying all the empty sites in your array. The detailed experiment is the experimental protocol is like this. So first, we initialize all the spin dimers into a singlet by putting them into together. And then we separate them to have a 3 microsecond automatic ramping time, which is adiabatic enough to prepare the ground states of the target parameters. And then we do a 1 nanosecond diabatic ramping back to do the polyspin blockade, because if two spins they are anti-parallel, you can move them together, but if they are parallel, you cannot move them together. This one, mapping the spin state to the charge state in the system. And what we do is that in a single short run of the experiment, we can read out 3 dimers in this sequential way. So first, what we do is that we read out Q1. We name Q1 here because we only consider S and T minus in the system, and they can actively forming a ST minus qubit. So we measure Q1 first and then Q2. And after that, we swap the information between Q2 and Q3 to read the Q3 information through Q2. That's the reason is that Q3 is far away from our sensor, and to improve the visibility, we have to rely on the swapping gate between Q2 and Q3. Before we perform the experiment, there are 2 challenges in our setup actually, if you are familiar with. The first one is that although we have gate electrodes on the top of the device that we can control the chemical potential or the tunnel coupling in the system, we found that we have a very strong crosstalk. So the plunger gate that control the chemical potential can also changing the chemical potential of other dots. And if you change one exchange coupling, they can also change the other exchange couplings. What we need to do is that we need to have a matrix that converts using the linear combinations to convert these plunger gates and barrel gate voltages to a virtual set of plunger gate and barrel gate voltages to control the chemical potential and the exchange couplings independently in the system. The right figure you can see is that when we characterize the crosstalk in the system, that how the crosstalk is when we control the target exchange coupling in the system. The second challenge is that in this experiment, we want to make sure that we are changing all the spin gap at the same time and with the same energy. And actually, if you do not do the calibration, in the real system, you have different offset of spin gaps when you apply gate voltages. But after the calibration, we can make sure that all the dampers, they changing the energy splittings at the same time. So we can really change the Hamiltonian homogeneously in the array. Here, we first have an experiment in the 2x3 array. We fixed the horizontal coupling to be 1 micros. And then we changing the vertical spin gap by changing the vertical exchange couplings. So you will see that when you measure the triplet probabilities, you see that 0 triplet probability will be very high in the beginning because in the beginning the J perpendicular is very large. And then if you decrease the J perpendicular, you will see that you have more triplet in the system, and it just enters into the content antiferrometric states. And then if you increase more, you enter all the polarized states of the system. This is how we map our 3 damper systems into damerized quantum magnets. We can also count the average of the triplet numbers in the system. And we do see the step and the peak either in the average and in the variance of the numbers. And this can indicate we really have mimic the behavior of quantum phase crossovers in the system. The only problem here is that we find that the variance peak is very broad. It's much larger than the horizontal coupling 1 micros. And this, the problem is here is that we have a very strong spin coupling in the system. And what we do is we want to conquer these horizontal couplings. So we increase the horizontal coupling from 1 micros to 30 micros of the upper leg. And we do see that the intermediate phase of the contact antiferrometric states, the region is larger because it is controlled by the horizontal coupling theory. And we also collaborate with theorists Wutsu and Eugene. They do a numerical simulation and reproduce our experimental results. It proves that we can really changing the horizontal exchange coupling to change the phase diagram. We can also count the correlations, and what we see here is that the correlations is getting more negative and negative when we increase the horizontal exchange couplings. This is also coincide with our theory that you have more exchange couplings, it is more anti-parallels. And then we scale this setup to 2x4 array. And we also do see that we have 1 triplet popping out and down in this system. And what we can do more is that we can locate the triplet in the system by doing the redots of 4 triplet dampers at the same time. And what we do see that if you see here, the highest triplet, 2 triplet probability goes to the location where the 2 triplets on the outer side of the array. And the lowest probability of the 2 triplets probability goes to the setup where the 2 triplets are close to each other. It is also coincident with our theory because you think that because of fermionic systems, that the 2 triplets will repulse with one another rather than close to each other. Okay, to sum it up, we can really observe the signatures of magnetic quantum phase crossovers in our small setup, and we can change in the exchange couplings. And more things like spin-orbit coupling and temperature is under investigation. Thank you.
Okay, thanks. We have time for one question if it's a very short question.
I was struck by the 3 microsecond adiabatic ramp.